morning. Welcome back to Open Med School. In the last session, we have discussed about the resting membrane potential. Today, we will be discussing on the Nernst equation. Basically, the membrane potential depends upon the concentration gradient, and second is the selective permeability of the membrane to various ions. The major ions are sodium and potassium, and that is why we are discussing about it, but some contribution by calcium and other ions are also there. We will come with what is equilibrium potential and how to calculate it by using the Nernst equation. You can see the potassium is more in the cell, it is along with an anion, and the sodium is more outside and it is goes with the chloride. So chloride and anions inside and chloride outside produces electroneutrality. This is a law of electrical neutrality. That is, when the potassium attaches with the anions and the sodium attaches with the chloride, so that the electrical neutrality is maintained. This is approximate concentration of various ions. So I have already mentioned that one of the fundamental things for maintenance of resting membrane potential is the differing concentration, or the concentration gradient of various ions are important. The major ions we are concerned are the sodium and the potassium. The sodium is the major cation outside, approximately 140, and inside it is only 14. And the potassium, you can remember the reverse, inside is 140 and outside is 4. By the rule of 4, you can remember. And as you remember, the chloride attaches to the sodium, so the chloride will be more outside, approximately 100 to 120. So this is how you remember the various values. So I already mentioned the leaky potassium channel. Here this is a potassium channel through which the potassium is moving outside, but the anions are accumulating, and that will produce a inside negativity. Hope this is clear. So this is the cell. Inside contains more potassium, approximately 140 milliequivalents. So there is a concentration gradient, or the ions move out through the leaky potassium channel, and at the same time, as the potassium is going outside, inside becomes more negative. Potassium is positively charged, so potassium will try to get inside. So this is the electrical gradient. So the concentration gradient is opposed by the electrical gradient as far as potassium is concerned. Hope this point is clear. And these two gradients, chemical plus electrical gradients, are called electrochemical gradient. But there will be a time at which the chemical forces driving the potassium outside is neutralized by the electrical force. That is the force that is making the potassium getting inside. A particular voltage, there will be no transfer or ions moving outside and moving inside are equal. This is called the equilibrium potential, or the Nernst potential. So what is equilibrium potential? The potential of the membrane potential at which the ions moving outside and ions moving inside are equal, and there is no net movement of the ions. Hope this point is clear, and this is because of the concentration gradient and electrical gradient working together. And this can be calculated by using a modified Nernst equation. So this is a modified Nernst equation. This is the voltage of the membrane. This can be calculated by a constant, that constant is 61, divided by Z, that is a valency, into log concentration of the ion outside divided by concentration inside. So let us take the example of the Nernst potential, or the equilibrium potential for potassium. The formula is 61 divided by valency, that is 1. Potassium outside is 4, inside is 140. 4 divided by 140 will be 1 by 35. So 61 into log 1 by 35 is equal to 61 into minus 1.54. It approximately it comes 91.5, and you can see that the membrane potential approximately equals to or near to the equilibrium potential of potassium. The next session will be discussing about the action potential in excitable tissues. Hope it was useful to you. Stay tuned. Thank you.